Picture this. A rider taps their phone for a pickup at a busy curb. That simple, everyday action kicks off an absolutely massive, invisible chain reaction of technological handoffs. So, in this explainer, we're going to map out exactly how a robotaxi, an automated driving system, actually sees and navigates an entire city. Now, to understand how this works with zero sci-fi magic, we need to trace the vehicle's journey through 6 distinct layers. We'll look at the durable city map, live sensor evidence, predicting multi-agent chaos, the chosen trajectory, when certainty fails, and finally, the continuous loop. Let's get right into it. Layer 1, the durable city map. Before a vehicle even moves an inch, it relies on a highly detailed, foundational blueprint of the city. This basically establishes the strict boundaries of where it's even allowed to operate. What's really interesting here is the regulatory side. The National Highway Traffic Safety Administration, or NHTSA, defines this approved service area as the Operational Design Domain, the ODD. That means the vehicle knows exactly what jurisdiction it's in and what specific conditions it's approved for, way before it ever accepts your ride. It doesn't just guess where it can drive. It's completely bound by this pre-approved domain. And honestly, this illustrates the fundamental tension of autonomous driving. The whole system is built on reconciling the map's durable memory, how this city should be, with the chaotic, live reality on the street right now. To handle this tension, companies like Waymo build mind-bogglingly detailed custom 3D maps. We're not just talking about street names here. They encode local rules, like San Francisco's strict 10-mile-per-hour transit safety zones, or even highly unusual permanent features. For example, static mannequins standing on the sidewalk in the LA fashion district. By having that permanent geometry already memorized, the system won't freak out at a mannequin, and it can focus its live computing power on what really matters, actual moving threats.
Layer 2, live sensor evidence. As the vehicle approaches our pickup spot, that stored map just isn't enough anymore. It needs live evidence. To get that evidence, these vehicles use multimodal sensor fusion across 3 main tools. First, lidar paints a highly precise 3D point cloud of the geometry up to 300 meters away, even in total darkness. Radar cuts straight through rain and fog to instantly measure the speed and direction of objects. And cameras provide the rich color and visual context needed to read stoplights or street signs. Every single sensor has a weakness, but together, they literally cover for each other's blind spots to form a continuous awareness of the environment. So what does it do with all that data? Well, NHTSA categorizes this continuous monitoring as OEDR, Object and Event Detection and Response. The vehicle has to constantly detect objects, classify them, like figuring out there's a static obstacle in the lane, and prepare to execute a safe response. To really wrap our heads around this, let's look at a specific scenario. Imagine our robotaxi rolls up to a highly disrupted intersection. We have to ask our first big recurring question. Based on the map and the live sensors, what exactly has the system verified in this exact moment? Layer 3, predicting multi-agent chaos. At this intersection, the vehicle's verified data must now anticipate the completely chaotic, unpredictable movements of multiple independent actors. Here is the chaos it detects in a single millisecond. 1. A new unmapped work zone that totally contradicts its stored map memory. 2. A static delivery truck obstructing the lane. And 3. A dynamic cyclist rapidly approaching the crosswalk, all happening at the exact same time. Now, as Waymo engineer Vincent Van Houk points out, the system doesn't think or reason like a human driver. It mathematically cross-references these conflicting sensor inputs. It never completely trusts just the camera or just the lidar. It merges them to build this high-fidelity probability matrix of the physical world. Which brings us to our second big question. What is the vehicle predicting next? With the cyclist actively tracked and a truck confirmed as parked, the system calculates translucent branching probability paths. It maps out exactly where these independent actors might be over the next 3 seconds, essentially preparing for multiple futures at once. Layer 4, the chosen trajectory. All those crazy branching predictions and probabilities, they have to be constrained into a single, safe, physical maneuver. Waymo describes this continuous internal loop as sense, solve, and go. The system has sensed the environment, it's solved the routing through AI prediction models, now it must go. This is the handoff. It's the exact moment the mathematical prediction meets the physical world, the mechanical steering, the accelerator, and the brakes. To navigate our messy intersection, the system locks in a crisp, safe trajectory. It implements longitudinal control to slow down while calculating a lateral shift to physically steer around that parked truck. All the while, it makes sure to yield the right-of-way to the crossing cyclist. It is quite literally translating digital math into physical movement. Layer 5, when certainty fails. But wait, what happens when the math doesn't add up? What if the sensor data is fiercely conflicting, or the probability of a safe maneuver drops below allowable safety thresholds? This is our third and final reoccurring question. What happens if that knowledge is uncertain? Say that cyclist behaves completely erratically, or the new work zone totally blocks the road with no clear path forward. The system doesn't just guess and hope for the best. It shifts into a defensive failure path. Guided by those strict NHTSA frameworks we talked about, the vehicle is programmed to execute a minimal risk condition, or MRC. An MRC is a low-risk operating state. Simply put, if the vehicle cannot confidently solve the driving task, it will automatically resort to pulling over or coming to a safe, stable stop. It always prioritizes safety over finishing the trip. And this really shows the deep layers of safety involved. The vehicle is running continuous self-diagnostics. If primary systems fail, secondary compute redundancies instantly take over. The vehicle might also initiate a request for contextual remote assistance. Actually, let's be super clear on this. This is not a human remotely steering the car with a joystick. No way. The vehicle is just asking a remote human agent to provide contextual labels for a confusing scene, like a weird construction zone, before safely completing its minimal risk condition stop. Layer 6, the continuous loop. Navigating that disrupted intersection isn't just about finishing your current ride, it's actually about updating the entire system for the next one. When the vehicle safely clears that unmapped work zone, it doesn't just forget about it. It automatically flags the discrepancy between its durable map and the live reality. It safely reroutes, uploads that environmental change data, and instantly shares it with the entire operational fleet. The collective memory of every single robotaxi in the city gets updated in real time. It's like a hive mind. So the big takeaway from this explainer is this. A robotaxi never actually sees the whole city in one grand human-like image. Instead, it is a tireless engine of synchronization. It continuously loops stored map context, live sensor physics, operational design domains, and rigorous safety constraints millions of times per trip, turning all that data into repeated, millisecond decisions. Which leaves us with a really fascinating question to end on. When you look at how these systems constantly map, sense, and update each other, are we just building driverless cars to get from point A to point B? Or are we actually building a living, breathing digital nervous system for our city streets?